Great. Well, thanks very much for the invite to come to the event, and it's certainly always enjoyable to see how much has changed in 1 year as the whole industry has moved forward, and academia as well, and kind of taking a lot of these 5G concepts into the design phase as we look forward to upcoming standardization. So in today's talk, I want to go over kind of the design of 5G across services, and then really also want to begin by saying that we're not intending this talk to be a commitment to the characteristics or commercialization of any product or service, but rather kind of going over some of the key aspects of how are we designing 5G and what are the use cases we're going after, and what are some of the really interesting, we feel, technical approaches that can help drive to those solutions. So as we've heard from the other talks so far today, that we've really seen now this focus on three key use cases in terms of the mobile broadband. So that's the use case we obviously know very well from existing 4G LTE deployments. And as we look to 5G, how can we further enhance mobile broadband in terms of driving to enhancing that from an indoor, outdoor hotspot capacity, really driving bandwidth, latency, and new approaches to deliver that user experience. And then the other aspect, as we move to smart homes, smart buildings, we get into this wide area IoE or IoT. And so this huge proliferation of numbers of types of devices. And then moving into the higher reliability services. So as we try to increase the reliability in the wide area network, what are some additional use cases we can target and some of the performance in terms of latency and reliability? So if we bring those new services together, the hope is that we can also much better address some of these interesting vertical markets. So what I want to do in today's presentation is really go over some of the technical aspects across those different services and how we feel they interplay. Because as we've seen before, the goal of 5G is not to do everything perfectly at the same time, but rather, as we target to different use cases, how do we optimize the FiMac building blocks and how this kind of interfaces with a broader network? So if you look at, well, what's really changed? So we say, what's changed, even when 4G began getting designed in 2004, 2005 for the initial Release 8 deployment, well, what's changed in that time period? And we feel there's been key improvements in the RF and antenna technologies. That's why we're seeing a lot of talks these past few days on things like massive MIMO, spatial processing. So the improvements on the RFIC front, not only enabling new millimeter wave bands to be considered, but even how we approach the design for bands such as 4 gigahertz. And then improved radio processing from faster narrowband, wideband switching. So how fast we can do the switching between transmission and reception, how fast we can do acquisition. So fundamentally, time processing is getting faster, not only in an RF sense, but then also in a baseband sense. So as we drive to improvements in silicon, both on the network side and on the device side, not only does that improve power consumption, but it also allows us to drive to lower latency, faster turnaround time, and new FiMac algorithms that exploit that inherently. And then, as been also highlighted in a lot of the talks, the notion of the network virtualization and how we look at the whole core network in 5G and what's happening above the RAN, there's an opportunity not only to have the slicing per service, but then also to dynamically move what's happening at the edge versus what's happening in the core. So that ability to more dynamically configure where things are happening and how they're happening also fundamentally allows these improvements on the network side. And so the goal then, as we bring these different opportunities together, is to drive fundamental improvements in the user experience, the coverage, the cost efficiency. So I think from the operator perspective, we've heard a lot of feedback on the desire for energy efficiency and cost savings, and then also what can we do to improve the coverage and user experience. So not only to deliver, sure, higher peak rates when feasible, but really driving higher data rates throughout the coverage area. So as has been said before, it's more challenging to deliver 100 megabits per second everywhere than 10 gigabits per second in a short direct link. So delivering this high quality of experience, we want to do this across cell sizes, topologies, and new services, and then also to have new designs both above 6 gigahertz and below 6 gigahertz. So we see the kind of interplay and co-design opportunity as we're leveraging some of this new spectrum. So if we look then, so what are these different opportunities? So we look at the spectrum types and bands. So as has been said in some of the talks as well, the notion of designing not only for licensed spectrum, shared licensed spectrum, but then also unlicensed spectrum. So a native design designed to handle the different types of spectrum classes, but then also classically FDD and TDD across bands and bandwidths. So natively in 5G, we feel there's a need to really look at some of these interesting bands where we're going to design for wider bandwidth, such as 80 megahertz or 160 megahertz in the 4 gigahertz band, but then also, as we look to eventual legacy refarming, the need for 5G to support FDD solutions as well. And so we look at then, what are some of the target characteristics for how we design across these bands and bandwidths? And so a key example of that would be some of these lower bands where we have the deep coverage, mobility support, driving a high spectral efficiency, high reliability, wide area IoE. A lot of these are going to really benefit from the coverage of these low bands. If we look at then the classic between 3 gigahertz and say 5 gigahertz, the opportunity to deliver wider band TDD focused solutions for outdoor and indoor, mesh designs, and even having higher peak rates here, because here, even sub 6 gigahertz in licensed spectrum, we're going to get wide band. And then obviously natively designing for 5 gigahertz wideband is also a key component. As we drive this new 5G FiMac, we can also do assisted access into the unlicensed spectrum. And then when we look at mmWave, we have that huge opportunity of going to significantly wider bandwidth and then doing that for indoor and outdoor small cells and also access and backhaul integration. So then when we look at the overall approaches in terms of optimized waveforms, network synchronization to look at when do we want to be synchronous, when do we want to be asynchronous, having scheduled opportunistic transmissions, and then supporting a wider variety of network topologies, and then looking at, well, when do we want to be orthogonal, just like a OFDM-based modulation, and then also when are there some opportunities to leverage being non-orthogonal multiple access, for example, in certain uplink scenarios. So 5G, addressing these use cases and requirements, there's a variety of techniques. And what we do in this slide is kind of break that circle apart and show how we feel that as we're addressing the key use cases and driving for this design across services, they were able to see what are the different FiMac techniques from a RAN perspective that are useful in each of these scenarios. So we can begin with the enhanced mobile broadband, where the key component here is designing a lower latency, scalable numerology across bands and bandwidths, and doing an integrated TDD subframe design, which I'll explain in a few slides, where we're designing with a TDD-centric focus of what can I do for licensed and unlicensed spectrum as I design this TDD FiMac. And even leveraging fast SRF designs so that we have massive MIMO support built into the waveform. And then also having a device-centric MAC where we're minimizing the amount of broadcast. So this was also commented as we look to forward compatibility, how can we make a more lean design where there's less broadcast, there's more user-specific steered information. So that's the fundamental point of the 5G enhanced broadband, and then we look at to the other aspects of it. And one is mmWave. So as we drive to these much higher user throughputs, the ability to leverage the mmWave bands with integrated MAC across sub-6 and mmWave, access backhaul integration, mmWave beam tracking. And then we look at the wide area IoE, or what's also referred to as massive MTC. Here we have to look at a fundamentally different set of opportunities of low energy waveforms, optimized link budget, decreased overheads, and even managed mesh. And then we look at the high reliability use case. Here, how can we design to low latency, bounded delay, optimized PHY design, pilot, hybrid ARQ, and an efficient multiplexing of low latency with nominal. So then we take a step back and we say, how do we want to make this forward compatibility waveform? So yes, we want to design blank subframes and blank frequency resources, minimizing the broadcast, enabling future features to be deployed on the same frequency in a synchronous and an asynchronous manner. And then even allowing vertical service multiplexing, for example, high reliability here, multiplexing in. And then, as I mentioned before, the opportunity with mmWave is that we can co-design it with sub-6 gigahertz. And so here we see even on the mmWave, perhaps not having even the control channel could be going on sub-6 gigahertz in a tight, basically carrier aggregation type integration. So this compatible frame structure design allows us to address a variety of these use cases. So that's where we see when we take a step back and we look at, sure, there's a variety of use cases for 5G. There's been a lot of good discussions of how do we prioritize amongst those. But the point is that a variety of techniques can come together to do this in an integrated and phased manner. So the other part is this multi-connectivity across bands and technologies. So there's going to be a lot of continued investments in 4G. We can't stress this enough that as we're adding 5G, we're adding it to 4G. We're not trying to replace 4G. So the reality is that there's been a huge significant investment in 4G infrastructure. As new bands come online, that's the opportunity for 5G, both sub-6 gigahertz and mmWave. So this picture just paints a scenario of having 4G and 5G macro coverage, having that 5G above 6 gigahertz, in addition to 5G below 6 gigahertz with this tight integration, and leveraging small cells that also have 4G and Wi-Fi. So fundamentally, we feel the opportunity is not only multi-mode device with 4G, 5G, and Wi-Fi, but then also a multi-mode, multi-connectivity network. So the fundamental point is that even as Wi-Fi is improving, as 4G is improving, that we can use multi-connectivity to drive to a network that's really delivering 4G and 5G in unison. And that's where we show on the macro cell 5G below 6 gigahertz in addition to 4G, and then kind of rolling it out across areas to suburban, rural areas as well. So that's the point that 4G itself already has this multi-connectivity capability that allows 4G Wi-Fi interworking. And as part of that, when we introduce 5G, we're able to leverage that from day one to allow 5G, 4G interworking. So if we look then at the mobile broadband use case, so okay, let's take into the specifics. The key requirements, as I mentioned, this uniform user experience, where we want to really improve the distribution of data rates that are achievable throughout the area. So not only trying to, as I said before, go after peak rate, but also the network capacity, the cost and energy efficiency, and then, yes, also the user experience peak data rate. And so the technical considerations we feel are a scalable numerology and TTI to support these different spectrum and QoS requirements, massive MIMO to achieve high capacity, better coverage, low network power consumption, the self-contained TDD subframes, and this device-centric MAC. So we'll kind of go through these things one by one. So the first is this scalable subframe, where by having this relationship among the subcarrier spacings as we target different bands and bandwidths, we can then optimize the waveform numerology for particular use cases. So this is an example for a normal cyclic prefix, for example, for an outdoor picocell. If I was trying to cover 80 megahertz, I can do it with a subcarrier spacing of 2n. If I'm going to a much wider, say 160 megahertz bandwidth, I can do it with a wider subcarrier spacing to have a much more efficient waveform in terms of processing at both the network side and then also the device side. And then even going to millimeter wave to have this TTI and this subcarrier spacing scaling across sub-6 gigahertz and millimeter wave. So even continuing that, as we look to the numerology of millimeter wave, we want to look to the numerology of the sub-6 gigahertz and have this relationship. And one of the things that enables then is this numerology multiplexing, even across, for example, normal cyclic prefix and extended cyclic prefix from the same network element. So that's where having this millimeter wave synchronized design at a TTI level allows then this tight interworking on the MAC side. And then this timing alignment, even with the 1 millisecond LTE subframes, when we look at then the dual connectivity. So if we look then, so what are the opportunities then with regards to this scalable numerology? So one thing is on the FDD side, we would fundamentally decrease the number of HARQ interlaces. So one of the things about HARQ is the storage requirements that entails, and then the RTT turnaround time between the successive retransmissions. So in 5G, we have an opportunity to design that, taking into account the faster processing on the UE side and the eNoB side, so we would drive to the shorter HARQ RTT. And then even in TDD, by designing the ACK into this integrated subframe, so not only including the data portion and a guard port and the ACK, we now have this compact transmission covering TDD as well. So in principle, we could even have the successive transmission on the following TTI. So this order of magnitude lower HARQ RTT results from this more optimized design. So it is one of those things when we look, hey, what changes in this new G? The ability to have this faster time processing and wider bandwidth scalability is something we would inherently exploit in 5G. And so this is where we can drive down the HARQ latency and the storage requirements and the faster processing time. And then in the self-contained TDD subframe, we have this integrated approach to licensed and unlicensed spectrum, massive MIMO, and then decoupling the uplink downlink data rate ratio from the latency requirement. So we're able to now not have this notion of the downlink subframes being exclusively downlink, waiting for an uplink subframe. Instead, we can design in a downlink to uplink within an integrated subframe. And as I mentioned before, as we're looking at the scalable numerology, the other thing is what is the TTI we need to achieve? And as we look to, say, nominal TTIs and ability to do a more efficient bundling, we also have the ability to design these shorter, low latency TTIs that are explicitly targeted to low latency, high reliability communications. So this provides various levels of QoS, and then the bundling TTI design for latency efficiency trade-off. So that was one of the points when we look at the 5G requirements that were discussed a lot last year. And the point is, we can't achieve it all at the same time. So there's fundamental trade-offs where a more efficient design driving to lower latency, those don't always go hand in hand. So as we drive to shorter times, we inherently have less time diversity. So the question is, how do we compensate for that in the overall system design? So that's where allowing some of this efficient multiplexing, efficient bundling, and then also we don't presume every single transmission is going to be these very short bursts, but rather we're going to have different sorts of TTIs based on the link requirements for a given transmission. So that's the service-aware TTI multiplexing. So here we can kind of do a deep dive on the self-contained TDD subframe itself, whereas, as we said, it decouples the HARQ processing time from the uplink downlink configuration. So in this example here, we have the control signal followed by the data, followed by the uplink. So this would basically be obviously the control, the data, the pilots, and then the ACK channel itself. And then here we can also look at how would we further evolve this structure to also incorporate, for example, SRS for massive MIMO, or stuff for unlicensed operation in terms of CCA, in terms of D2D operation for device-to-device communication, for mesh, for coordinated multi-point processing. So when we look at these aspects of 5G trying to address this broader number of use cases, broader number of scenarios, that's where one of our goals here is to be able to phase these features in over time. We don't think it's feasible to standardize every single aspect in the first release of 5G. So as we look at how can we phase things, one point is how do we do inherently a more forward compatible design? How can we then have the foresight to say, let's specify a subframe structure that allows us to bring in these other features over time, but do it in a way that fundamentally is part of the same system. So we can leverage the initial network deployment, add functionality over time. And one of those things then is having these interchangeable TDD subframes that each themselves can be optimized for particular use cases based on the appropriate signals. And so this is where the point is having these headers associated, for example, with clear channel assessment, hidden known discovery protocols for 5G unlicensed spectrum operation. And so this is where the opportunity lies with kind of taking a step back and saying, okay, how can we design this more forward compatible, flexible subframe structure? And a lot of also discussion on waveforms. We feel that fundamentally OFDM continues to have inherent advantages with regards to for example, designing a system with scalable bandwidth based on FFT size and bandwidth we're trying to achieve, low latency, wide channel bandwidth, low complexity per bit. And we can't forget why we moved to OFDM and 4G in terms of the opportunity for SDMA, MIMO, and using the cyclic prefix with appropriate filtering to achieve also the orthogonality among users, and then move to this spatial multiplexing aspect. And so the other thing is then, as we look at the link requirements, we can look very carefully at the transmitter and receiver filtering to say, hey, how do we want to filter the OFDM based on particular multiplexing and link needs? So we do feel that OFDM itself, in terms of how it does the time frequency grid, fundamentally has key advantages. At the same time, we do feel that as we look to some of the different use cases and their requirements, there's the advantages to sometimes being asynchronous, because synchronism there's a price associated with becoming synchronous and having that inter-user orthogonality. And so, for example, a resource spread multiple access approach where we have a waveform that's inherently non-orthogonal across users has some advantages for certain types of traffic. For example, short bursts of data communication where you just want to transmit it, so turn on, transmit, turn off. We don't want to spend the time and energy becoming synchronous and maintaining that orthogonality. So this is where an RSMA type waveform, where it's spreading across resource elements in time and frequency, allows us to have this non-orthogonality as well. So if we look at some of the aspects of going to some of these bands, if we go back to that original frequency table I showed, I said, hey, we're trying to design, for example, for 4 gigahertz type bands. One of our points is that we don't want these new bands to only be used in kind of very localized small scenarios. For a given deployment, we want to maximize the coverage we can achieve in that 4 gigahertz band. As part of doing that, we would fundamentally leverage massive MIMO at the eNode B, that is at the infrastructure site. And so here we're comparing 2 curves. One of them is a 20 megahertz example where it's 2 by 2. And then another example is where it's 80 megahertz bandwidth at 4 gigahertz. So we've changed the carrier frequency, and we've increased the bandwidth. So, but we've spread the energy, we've decreased the PSD over that wider bandwidth. So what we're trying to show here is that if we're trying to decrease the network energy consumption, one of the points of the opportunity in 5G is to spread that energy further in spectrum. So we're going to decrease the PSD by spreading it out, but we're going to use the spatial processing at the eNode B through massive MIMO to compensate for not only is the 4 gigahertz band have worse propagation than 2 gigahertz, but we've also not increased the network energy consumption. We're not transmitting 4 times more energy here. We're spreading the energy wider in bandwidth. And the point is we are able to achieve then this better data rate distribution by moving to a 4 gigahertz design and natively using massive MIMO. So that's one of the points here, that as we look to designing bands like 4 gigahertz, we want to enable those bands to not only be small, like capacity offload sites, but then also to deliver coverage. So this simulation is actually over a 1.7 kilometer intra-site distance in the 4 gigahertz band. So this is something where we want to leverage the same cell tower locations and transmit power as legacy systems, but deliver, as I said before, to numbers approaching 100 megabits per second everywhere by using this spatial processing. And then we can look at an extreme scenario where instead of 4 gigahertz, let's look at a millimeter wave band, such as 28 gigahertz or higher, where we can say, hey, is it a standalone millimeter wave access scenario, or is it a co-located of millimeter wave with 5G sub 6 gigahertz? Is it a non-co-located scenario where I have sub 6 gigahertz here and millimeter wave in a different location, or integrated access backhaul and relay? So we feel that perhaps this might be a more challenging use case because of the propagation characteristics of millimeter wave, and so some of the other ones are more interesting. And one aspect is really leveraging the millimeter wave not only for access, but then also for the backhaul site-to-site communication link. So if we look at millimeter wave, there's a variety of techniques for beam search and beam tracking that are going to be inherent to efficiently operating and closing that link. The other aspect is that the network itself becomes more interference limited. So you're able to use the directional element of the millimeter wave base station to achieve the SNR distribution as you steer to the different users. But the point is then, how can we do some interference reduction based on coordination across the cell sites? So this is one of our network simulations where we're looking at the ability and the benefits from a more coordination across these cell sites. So it's something when we look at having an adaptive network, having integrated access and backhaul, that we feel millimeter wave opens up interesting degrees of freedom because it does become this more spatially directive communications link. And then the other thing is there's been a lot of focus on user plane. So there's a discussion a lot on the network, how we can make a better network in terms of network slicing, virtualization, those sorts of things. But the other aspect is the actual control plane from the RAN itself. So how can we make not only addressing the user plane aspects, but what can we improve in terms of mobility, in terms of device state? So this is an example we call the device-centric MAC, where fundamentally we can change how we do mobility. So one example here is this what we call SIB on demand, where the SIB transmission is based on a SIB transmission request from the UE, so that we're really minimizing the amount of broadcast. So that's why this is similar and the same flavor of our minimized broadcast, the lean transmission approach. So here we're only transmitting a periodic sync signal, and then if a user wishes to transmit, he transmits a SIB transmission request that's heard by multiple sites, and then he gets the transmission SIB, and then if there was no SIB transmission request, there wouldn't be that additional transmission. So the point is really minimizing the amount of transmissions coming from the network side. And this also then allows transparent mobility within a device-centric zone. So if you have a zone of multiple sites, as the user is moving around there, then the control plane processing is coordinated across those tightly integrated sites. So one of the opportunities we feel is if you have some cluster of sites or even a large number of sites that are really tightly controlled in terms of the link between them, then we can have new approaches for how we do the control plane and the mobility management with this on-demand system information transmission. And so when no devices are around, the base station only provides a low periodicity beacon signal. So this also decreases the energy consumption on the network side. And when a few devices enter the coverage area, the base station provides a system information via this on-demand unicast. And if there are many, many devices who enter a particular location, or the SIB changes, the base station can revert to a more classical broadcast mode. So this is the point that as we look to not only user plane enhancements, but also control plane enhancements and a more tightly integrated picocell network, we can revisit how we do some certain mobility procedures for the network energy consumption and for the efficiency of the network. And so the other thing is then, if we explicitly design for high reliability, what are some of the techniques we would do there? And so this is the high reliability, low end-to-end latency is another requirement, and minimal impact to nominal traffic. So our point is that we don't think it makes sense to design in an FDM sense, a location, a certain amount of frequency allocated specifically for very high reliability traffic. We feel we want to find a way instead to multiplex the low latency traffic with the nominal traffic. So certain devices and certain services will require very low latency, others won't. And so in terms of the trade-off between efficiency and reliability, we'll show that it's important to have an integrated nominal design with the high reliability system design. And some aspects are how we do new PHY coding, forward error correction, and a link adaptation framework for efficient multiplexing, and an efficient hybrid ARQ structure for this fast turnaround time. So this low latency requires these very short TTIs and an approach to get that fast HARQ turnaround time. And then also the diversity orders. This was mentioned in some of the talks about leveraging multiple site transmissions. We think that's another key point, that it's one thing to design a low latency link. The other thing, as we're looking at reliability and availability, we really want to leverage classical, multi-site transmissions, and then transmissions from a wider variety of device types. And so that also has new link adaptation paradigm for this low error rates. So if we take a step back and then we look at, we're trying to design PHY-MAC for this bounded delay. So there's a certain point after which we're going to say that didn't meet the transmission deadline. And so here we're looking at packet drop, not only when something fails at the receiver, but then also when it misses the transmission queue deadline. So if you look at the queuing theory of trying to drive to this low latency, high reliability, then that's where we're looking at both losses on the transmit side and the receive side. And so then these are some of the results that come out of that analysis, where we say, in this example on the left, I'm comparing a total bandwidth of 10 megahertz to a total bandwidth of 20 megahertz for a reliability of 10 to the minus 4 in terms of packet error rate. And I'm putting a certain hard delay bound at different values. So this is delay after which we're saying it was an error because it didn't meet the bound. And I'm plotting on the y-axis the actual capacity for the high reliability case. And so the point is, here I've doubled the bandwidth from 10 to 20, but I've got more than a 3x gain. So the reality is that as we go to this wider bandwidth, we're actually further improving the capacity by more than the factor by which we increase the capacity. And so this really makes the case that the wider bandwidth is providing these capacity benefits, partly because of the scheduling where you have to get these transmissions done. Whereas on the right side here, we're showing different reliabilities, 10 to the minus 2 and 10 to the minus 4, and showing the trade-off of bandwidth and the drop in reliability. So here the point is we look at fundamentally these trade-offs of how we can do a more efficient co-design of the nominal and the mission critical. And then the last topic I wanted to address was this Internet of Everything requirements, where here we're trying to drive these large numbers of low power devices. And here we have superior coverage for remote deep indoor nodes, low power consumption, better support for low bursty rate communications, and scalability to enable massive number of connections. And so some of the key approaches there, as I mentioned, on the waveform side, moving to a non-orthogonal approach on the uplink, and that allows distributed scheduling, and it also allows us to avoid the energy costs of establishing synchronization. And then the other point is on leveraging multi-hop device to device. So an IoE type mesh where we have a downlink direct signal, but to close the uplink, some of these devices might not have PAs, they might not be able to make the link all the way back to the site. So then if we finalize here on our final slide, where these were the different approaches that we showed for some of the key target areas as we look at, okay, what are the 5G goals across massive, the enhanced mobile broadband, the massive number of devices in terms of wide area IoE, the mmWave ability to leverage that new band and new spectrum, and the high reliability. So we feel that by having this framework of approaching the different use cases in a systematic way, we can still kind of roll out the commercialization and the standardization based on feature phasing, but do it in a forward compatible way that allows us to address these use cases over time. So thanks very much. Yeah, happy to take any questions.
Yeah, thanks a lot, John. I think we got a quick overview here of a complete air interface in 25 minutes. I think we have to save most of the question for John for the panel, but we can take one question here if we have. Do we have David?
Thanks for a good presentation. The question I've got is regards the capacity of the system.
Yep.
When you've got that high reliability. So you had the curve which had a 10 and 20 megahertz. I think on the y-axis it was the capacity of the system, which looks like it was of the order of around 2 or 3 megabits per second in a 20 megahertz bandwidth.
Yep.
Did I read that correctly? And what would the spectral
yeah, so we were
efficiency be?
showing, to quickly show that, we were taking an extreme example of a 256-bit control signal every 10 millisecond for 40 machines. So that's 1 megabit per second. And we took a worst case where these users were all at the minus 3 dB cell edge. So that's why from a spectral efficiency standpoint, the users were actually all in a bad coverage area to kind of make this trying to look at the worst case scenario.
Okay.
So in this example, we weren't trying to drive to an explicit net spectral efficiency, but rather focus on what are these trade-offs in bandwidth, reliability, and then and the hard latency bound. Because the point is that the fundamental nominal design will be still focusing, like 5G itself is going to be lower nominal latency and lower in an average sense. It's going to target average lower latency. As we target to a hard delay bound, it's a different sort of optimization criteria.
So I think we need to break here. So thanks, everyone.